This topic that I'm going to start right now is one of my favorite topics because it has a lot of real applications. So in reality, your system does not have only one pipe size, right? It is consisted of multiple pipe sizes and different shapes of pipes that are connected to each other through different loops or different fixings and junctions. So if the pipes are connected in succession, as you can see on this sentence over here, the system, we call it the system is in series. So as you can see on the top photo, you have three pipes with three diameters, 1, 2, and 3. And these pipes are connected to each other using different fixings, right, that have minor head losses. For example, this would be one and the other one would be over here that connect different pipe sizes to each other. Now, if the pipes cause the flow to divide into different loops, the system is in parallel. As you can see in the bottom photo, you have two different pipe sizes over here and over here, 1 and 2. And there is a loop. So the flow is divided into two branches over here. And as it goes through the loop, again, it is divided into two branches as well, right? So this is called the loop. And whenever you have a system like this, your pipe system is in parallel. And for the top photo, it's in series. So what we are going to learn today is how to analyze these types of systems and how to find head loss due to different components in these types of systems. In order to solve problems when it comes to systems having pipes in series, we need to use two fundamental equations. One would be continuity equation and the other would be energy equation. A continuity equation is pretty easy. Flow rate, or I should say volumetric flow rate, is equal in each pipe section when pipes are in series, right? Why? Because diameter is going to be different and velocity is going to be different in each section of these pipes that you see over here. So, and because flow rate is cross-sectional area times velocity, flow rate at each section, 1, 2, 3, is going to be equal. So that's the first type of equation that we write when we have pipes in series. And then after that, we need to write energy equation. An energy equation has a head loss. So the total head loss for the system for pipes in series would be the sum of the friction head loss or pipe head loss for each segment of the pipe plus the minor head losses or component head losses. I'm going to say minor head losses for the system. So, and as you can see, you can write the energy equation for inlet and outlet sections A and B as I have written already, and head loss would be summation of pipe head losses for different pipe segments, pipe sections, and also plus summation of component or minor head losses, component head losses for different components that you might have. For example, here it might be some flanges or a valve or whatever, or here it might be something else. All right, so as you can imagine, also before I forget, this should be FHF, there we go. As you can imagine, compared to having a single pipe, this problem is a little bit more complex because you need to calculate the value of F, friction factor, and the value of Reynolds number for multiple pipe segments with multiple diameter. And because the diameter is different, friction factor and Reynolds number is totally different for each pipe, right? So that's when you use computer to make your calculations faster and faster. For pipes in parallel, it is also easy as well. Continuity equation requires that the summation of flow rates in pipe 1 and pipe 2 be equal to the flow rate in point A or section A and section B, right? Because basically the flow divides over here into two sections, into 1 and 2, and then comes together over here as 1 and 2, okay? So that would be our continuity equation. Notice that there's a plus sign between 1 and 2, okay? And then the energy equation can be written as you are familiar with. There's one important point in here. Since the fluid, water, will always take the path of least resistance, the amount of flow through each branch pipe will automatically adjust to maintain the same head loss or resistant to flow in each branch. As a result of that, for each length in pipes 1 and 2, we require head loss to be exactly equal to each other. So we are going to consider head loss in pipe 1 over here and over here to be exactly equal to each other. And based on the information that we have, using this, the analysis of a single loop system, like what you see in the photo, is very straightforward and is essentially based on satisfying the equations that I have written on this slide. This slide serves as a review of what I just told you in the previous section and how to solve problems when you have pipes that are in series or in parallel. In general, the flow must satisfy two equations. One is continuity equation, and the other one obviously is the energy equation. The order in which you apply these two equations depends on the type of problems that you have, number of pipes that you have that you're going to solve some examples on. Also, just for your information, I have provided a summary of how to calculate head loss for pipes in series and pipes in parallel. Now that we know this, we are going to go ahead and I'm going to show you a couple of examples so you are familiarized with these types of problems. This example is related to pipes in series. So we have a galvanized pipe connected to a reservoir to a tank. The diameter of the larger pipe, this one, I'm going to show it with D, is 6 inches. And the diameter of the smaller pipe, this pipe, I'm going to show it with D prime, is 3 inches. Okay, now what we're going to find is the initial discharge of water. So since we are going to find discharge, then this is a case 2 problem, and it involves some guessing. All other values have been given to us. Notice that we have head loss due to the filter at C. So here there is a filter, and the head loss coefficient for that is 0.7. We are going to neglect the loss at the gradual contraction at D, and we have the value of kinematic viscosity for water. In case of S, for galvanized iron, has been given to us. It's 0.0005. Perfect. Now, we're going to start from energy equation, obviously, and this is going to be our section 1, and section 2 is going to be at the end of the smaller diameter pipe. I'm going to call this 2. So let's write down the energy equation. It would be something like, again, elevation head at A plus all the other terms, and then you can simplify based on the values that you have. Okay, now we can also write continuity equation to find the relationship between velocities. So I'm going to write the continuity equation between the pipe with larger diameter and the pipe with smaller diameter. So prime is going to basically demonstrate all of the variables in the smaller diameter. So if I write it down, it would be velocity in the larger diameter times area, which is P, and it is what's the area, what's the diameter? 6 inches. Okay, 6 inches to the power 2 is equal to velocity in the smaller pipe diameter times P pi over 4, 3 to the power 2. Perfect. So if you do some algebra, then you'll find out that velocity prime is equal to 4 times velocity. Okay, and it does make sense. The smaller diameter has larger velocity. And also notice that velocity at E is the same thing as velocity prime. Okay, now what I'm going to do is basically write down the energy equation in terms of velocity in larger pipe again to simplify, to actually reorganize it a little bit. So the elevation difference is 13 feet. So it would be 13 feet over here equals, instead of v prime to the power 2, I'm going to write 4v to the power 2 divided by 2 times 32.2, because we are doing the US customary units, and plus head loss. Okay, so I don't have the value for velocity, I don't have the value for head loss. This is as simple as this equation gets. So I'm going to move forward and write the HL. HL is my head loss, and I have friction head loss, and also I have minor head loss as well. So if I write it, I'm going to start with the friction head losses. So friction resistant F for the larger diameter pipe, and the length of that is 14, and diameter would be 6 divided by 12 to convert it to feet, times the velocity in the larger pipe to the power 2 divided by 2g. And by doing so, I just realized that here I did not convert these diameters to feet. So let me correct it. It should be 6 divided by 12 to the power 2 to the power 2, and this should be 3 divided by 12 to the power 2. But the final relationship between v prime and v is the same thing. That's not going to change. Okay, so let's continue writing HL. Now, the friction term for smaller diameter pipe, it would be F prime. Length of that would be 3. The diameter would be 3 divided by 12. And velocity, instead of v prime, I'm going to write 4v to the power 2 divided by 2g. So these were the major head losses. We also have some minor head losses as well, right? Minor head losses would be the head loss due to entrance over here, which can be written as 0.5 times velocity to the power 2 divided by 2g, plus there is an elbow over here that we need to consider. Notice that although the problem statement has not given anything about elbow to me, I know that if there's an elbow, I need to consider that elbow because the problem statement specifically told me that neglect the loss due to gradual contraction. So it would have said something if it wanted me to neglect elbow as well. So I'm going to consider an elbow as well. K for elbow would be 0.9 based on table 10.5 if I'm correct, and again would be velocity to the power 2 divided by 2g, plus next is the filter at C. We have KL for that. It is 0.7 velocity to the power 2 divided by 2g. And also there's an open valve over here, F. It says here the open valve. So again, if you refer to the table 10.5, you will see that for open valve, K, or the coefficient, minor head loss coefficient, is 0.19. Notice that this time velocity is velocity in the smaller pipe, so 4v to the power 2 divided by 2g. These are all terms velocity, minor and major. So if you do a little bit of reorganization and cleaning of this equation, HL can be written as 28f plus 192 f prime plus 15.64 times velocity to the power 2 divided by 2g. Okay, I'm going to actually move to next slide and continue. Now, if I plug in the expression that I found for HL into my energy equation, after doing some algebra, what I will get is 837.2 is equal to 28f plus 192f prime plus 31.64 times velocity to the power 2. Okay, now this is the equation that I need to solve, but the problem is that there are 3 unknown variables, f, f prime, and velocity. So in order to basically be able to solve this equation, I need to guess 2 values for f and f prime. F is related to friction losses in the larger diameter pipe, and f prime is related to friction losses in the smaller diameter pipe, right? Okay, we can calculate the values of Ks over D for the 2 pipes, right? So because we have the value of Ks over D would be 0.0005, which is in feet, divided by 6/12 would be 0.001, and then ks over d prime, if you calculate it, would be 0.002. Nice. Now that we have these, we can go ahead and guess f and f prime based on Moody diagram. I'm going to go to Moody diagram to show you how it looks like. Okay, so first of all, I'm going to find the relative roughness values on the second y-axis of Moody diagram. 0.001 is here and 0.002 is there. Now, what would be a good guess? A good guess would be an f that falls in the almost linear part of Moody diagram, the here or here. So what I'm going to do, I'm going to find a ruler first of all, and then extend this linear part until it intersects with f. So this would be, that was a very bad line. And believe me, it is not easy on this screen to use a ruler. So I'm going to do my best once more. There we go, way better, acceptable. And then the other one would be something like this. Okay, I'm not going to be very picky about it. Based on this, I'm going to say that my first guess for f is going to be 0.0, let's say 21. Yeah, it's very close. Okay, and then the second guess is going to be, which is guess for f prime, is going to be what it would be 0.024. Okay, so these are my first guesses for f and f prime. Now let's go back and plug them into the equation that we have. Okay, so based on our guesses for f and f prime, I'm going to put them in equation star on your screen, and I will be able to find velocity. Velocity in the larger pipe, or v, would be equal to 4.767 feet per second. And then, of course, velocity prime is just 4 times velocity, which would be equal to 19.06 feet per second. Okay, now that I have a value for velocity, I can go ahead and calculate Reynolds and Reynolds prime, right? If you do that, and I'll let you to check these values, Reynolds would be 2.25 times 10 to the power 10 to the power 5, sorry. And then Reynolds prime would be 4.5 times 10 to the power 5. Okay. Now again, based on k sub s over d's and k sub s over d prime and Reynolds prime, you can go to Moody diagram again to double check f and f prime. If you do that, I'm not going to do that, you can double check. Based on these Reynolds numbers and these relative roughnesses, the values that you would find are f exactly 0.021 and f prime 0.024. So it turns out, as long as your guesses are in the linear part of the Moody curve, then usually it's going to converge based on your first trial. You don't even need to do a second trial. So we are going to accept these values and based on the velocity calculate flow rate, which is equal to area times velocity, and the area of the larger pipe would be times velocity 4.767, and the result for this would be 0.936 cubic feet per second. But the problem statement asked us to convert the flow rate into gallons per minute. Gallons per minute. So to do that, I'm just going to write Q is equal to 0.936 cubic feet per second, and then do the conversion. 7.48 gallon would be 1 cubic feet, and then second to, or minute to second, would be 1 minute 60 seconds. The final answer would be 420 gallon per minute. Perfect. And this is the value of flow rate that we were asked to find. All right, this is a good example of pipes in parallel. Also, it is a good example of minor head losses. So first of all, what I want to do is to mark down all the components that we need to consider for minor head loss. Let's talk about it. So we have a component over here called T. T's are usually used to connect different pipes with different diameters together. And there's another T over here too. So if you go to table 10.5 to find the coefficient, the loss coefficients for different transitions and fittings, you will see that there will be two KTs for T's. One would be if the flow goes in this direction, and one would be if the flow goes in this direction. Let me change the color so these are represented by different colors. This not a good color again. This direction. Okay, so for this scenario, this is basically when the flow goes straight through. KT in your book is suggested to be 0.4. Now, if the flow goes to the side outlet, this one, KT is suggested to be 1.8. Okay? Now, what are the other components in this system? We have a filter over here, and the K for that filter has been given to us, so we don't need to look it up. We have a globe valve over here. Again, you can go to your table 10.5 and you will find that the K for the globe valve it's KV and is equal to 10. That's for branch number 1. For branch number 2, again, we have the T's, and also we have two elbows. Here are the two elbows. One is over here, and one is over here. These are 90 degrees elbows, so KB for these would be 0.9, and it's in the last row of table 10.5. In addition to that, we have one gate valve over here. For this gate valve, if you go to table 10.5, I'm actually looking at it. It depends if it is wide open or half open. If it's wide open, which in this case is wide open, then the value is equal to 0.2 in your book. But since I've already, in my note actually, I considered the value of 0.19. So we are going to consider the value of 0.19, but in your book it is 0.2. Okay? So we have all the coefficients, minor head loss coefficients. Now let's go ahead and read the rest of the problem. The 100 millimeter diameter pipe, which is the larger pipe and branch number 1, has a filter and a globe valve on it, and the 50 millimeter diameter diverter pipe has a gate valve on it. Okay, the pipes are made of galvanized iron, so we can look up K sub S from table 10.4, I think. We are going to determine the flow through each pipe and the pressure drop between points A and B, as you can see on the photo, when both valves are fully opened, and KL has been given to us, and specific weight of water and kinematic viscosity of water has been given to us as well. What I'm going to do is I'm going to start with continuity equation. Remember that for parallel flow, flow rate would be equal to flow rate summation of flow rates at each branch. So branch 1 flow rate would be velocity at branch 1 times area of branch 1 plus velocity at branch 2 times area of branch 2. Okay? If you do that, we can actually quickly write down the areas over here using the given values of diameter or radius. (0.025 to the power 2). So if you do a little bit of algebra and simplification, this would be 15.279 equals 4 times velocity plus velocity 2. All right, so this is the first equation that we got from continuity. Now, we know that for parallel pipe systems like this, head loss in each branch should be equal. So let's calculate head loss in branch 1 and branch 2, and then equate them to see what we can find. Hopefully we can find a relationship between velocity at 1 and 2. So in that case, we can solve the continuity equation. Now, branch 1 has flow through the two T's, as I said, the filter, and the fully opened globe valve. So I'm going to use the Darcy-Weisbach equation to find HL1 for branch 1. It would be F1, and this F is resistance factor for basically branch 1. Then it's going to be 3 meters divided by 0.1. Velocity 1 to the power 2 divided by 2g. Plus, we have two T's, right? So I'm going to say 2 times, and then coefficient for T's is 0.4 because it's a straight flow through. Velocity 1 to the power 2 divided by 2g. We also have a filter. We have actually the equation over here, so would be 1.6 velocity 1 to the power 2 divided by 2g. And what else? We have a globe valve, and globe valve, the coefficient is 10. And that is it. So we can do some algebra and simplify this equation and write it as 30 F1 plus 12. Let me write it a little bit better. F1 plus 12.4 times velocity branch 1 to the power 2 divided by 2g. Okay, we can do the same thing for branch number 2. And branch number 2 has flow along the branch of two T's, which is the side flow. So K would be different. Then we have two elbows and a fully open gate valve. So you can do the same thing and write this equation. I'm not going to actually write it down. You can try it by yourself. I have actually given you all the values for that. So if you do that, like HL1, you're going to end up having an equation like 140 F2 plus 5.59 velocity at branch 2 to the power 2 divided by 2g. Okay, now also remember that we require that the head loss in two branches should be equal. So I'm going to equate these two head losses, and it would be 30 F1 plus 12.4 power 2 divided by 2g should be equal to 140 F2 plus 5.59 2g. All right. This equation has four unknowns, F1, F2, V1, and V2. So we need to guess some values for F1 and F2. Because we don't have the value of D, we cannot calculate relative roughness, so we need to just guess values for F1 and F2. Your question might be, how do we guess these two values? Usually you can guess some like intermediate values for F1 and F2 at first. What are the intermediate values? Something from 0.015 to 0.025 to 0.03. These are intermediate values of F. So what I'm going to guess is, let me change the color over here. My guess for F1 is going to be one intermediate value of 0.02, and my guess for F2 is going to be another intermediate value of 0.025. Okay? Based on this, I can put it into this equation, and then I can find a relationship between velocity at branch 1 and velocity at branch 2. And then once I have this, I can put it in this equation over here to find the velocity. So I'm going to go ahead and do this in next slide. All right, so I've done what I said. based on the values of F1 and F2 that I guessed, I calculated velocity 1 and 2, and now I'm in the check process. I calculated Reynolds based on the velocities, I calculated K sub S over D1, and now I went to Moody to find out, to check my guessed F1 and F2 and to find new values for F1 and F2. It turns out that F1 and F2 would be, based on Moody, F1 would be 0.022 and F2 is equal to 0.027, which are not in the range that I'm looking for, so they're not exactly equal to what I wanted to. What I'm going to do is to repeat the calculation. So now these values are my second guesses. Okay, so I'm going to repeat everything with these values. I'm going to calculate velocity 1 and velocity 2, which, if you do that, it would be 2.95 meters per second and 3.48. And then calculate Reynolds number 1 and Reynolds number 2 based on these. Imagine that I've done that. And then calculate based on Reynolds and based on K sub S over D, you will find new values for F1 and F2. I've already done that, and F1 and F2 are basically very close to what I had. Okay, so I'm going to accept these, and these velocities would be the final velocities in branch 1 and branch 2, and I can simply use the equation Q equals to AV to calculate flow rate for each branch. Now, the only thing that remains is calculating pressure difference between points A and B. In order to find the difference in pressure between points A and B, we just need to write energy equation, because that's the equation that has pressure terms in it, right? So between points A and B, pressure, or between sections A and B, pressure divided by gamma, which is the pressure head, plus velocity head, plus Z, and it ends with loss, head loss. So let's do some simplifications. The pipe is horizontal, right? So Z's basically cancel each other out. Velocity. Both sections A and B are on the same pipe. The diameter is the same thing, okay? So the velocity is going to be the same as well. So velocities cancel each other out as well. The only terms that are here are pressures. So I'm going to write pressure A minus pressure B divided by gamma equals HL, or PA minus PB equals gamma HL. Okay, now how to find HL? HL, in order to actually find this HL over here, you can use either the equation for HL1 or the equation for HL2. Okay, so HL, because we already know that HL1 is equal to HL2, it doesn't matter which equation you use, you can use either of them. So what I'm going to use is HL1 with the value of F and velocity, or basically F1 and velocity 1, that I found out in a previous slide. So writing down this equation, it would be, again, PA minus PB equals gamma of water 9810. Now HL, I'm going to write HL like it's 30 times F1, and F is 0.022 plus 12.4 times velocity to the power 2. Velocity I found to be 2.95 to the power 2 divided by 2 times 9.81. Okay, so if you calculate this, it would be 56.8 times 10 to the power 3 Pascal. And this is the difference in pressure between point A and point B. Now you can also use HL2 equation, and you will get the same answer.